we're going to go ahead and, well, ideally all of you guys got the remind text / Blackboard announcement. I changed my mind and decided I wanted to cover differentiability before the test so that we go into next unit when we learn derivatives already knowing differentiability. So it kind of bridges limit definition of a derivative and taking the actual derivative. So next unit we're going to start off with derivatives of polynomials. So I want to do differentiability before that. So we're going to do differentiability today. It's a pretty simple concept. Some of you guys probably already know what it is. And then we'll just kind of recap the other stuff for our test. So you will have your test next class. When you come in, you'll turn in your stamp sheet and your review packet, and then we'll start the test right away. You do not need your calculator for this test. You won't get to use it, so don't bring it. I mean, you can bring it and then have it for good luck in your backpack or something. All right, so today we're going to start off by talking about differentiability. Keep the limit circuit nearby. We're going to start off just with our handwritten notes, good old-fashioned. And hopefully the projector works today. I can already see it.
How would you get your boards? It's a new board that has the pencils.
It's actually not the board, it's the port in my computer, but I have to send off my computer for like 2 weeks for it to be replaced. Yeah. I thought it was the port, but apparently it's the computer. Okay, so we're going to talk about differentiability. Every word in calculus seems to be expensive on. But again, this comes from our limit definition of the derivative. So let's go ahead and recap what that limit definition of the derivative is. I'm just going to go ahead and write it off to the side here because we'll be referring to it over and over again. So we had two options for our limit. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And then we had f prime of a equals the limit as ax approaches a of f of x minus f of a over x minus a. And we talked about how we can actually use either one of these. The top one is often most beneficial when we're trying to find the derivative of the whole function. And this bottom one is usually most beneficial when we try to find the derivative at a single point instead of a function to mimic every single point. So you can actually use both, and we'll talk about that more later today. Sometimes the A1 is quicker than the H1, but sometimes the A1 is harder to factor than the H1, even though it takes more time, it's easier to factor, things like that. But differentiability stems from our limit definition of the derivative. All right, so first let's talk about what it means to be differentiable. So a function is differentiable at x. A function is differentiable at x if f has a derivative at x. So differentiability, you can kind of see that differential derivative. So differentiability just means that it has a derivative. You can actually take the derivative. Which then what that means is there are some times in which it's possible for a derivative to be undefined, where we don't have the value there. Now, just if we said a function is continuous, if it is continuous at every point on its domain, we can just say a function is differentiable. A function is differentiable if it has a derivative. At every point on its domain. on its domain. So kind of like the same terminology as continuity, if it's continuous at every point on its domain, we can just say f of x is continuous. Likewise, if f has a derivative at every point on its domain, then I can go and say f of x is differentiable. But what it means to be differentiable at a specific point means it has a derivative. So when I say a function is differentiable, that means that every single point on its domain, you can take the derivative. All right. Now we have a nice theorem. Theorems, I haven't had that since geometry. A nice theorem in calculus, we're just going to say theorem, there's no fancy names for it. And this theorem says if f has a derivative at x equal to a, so if f has a derivative at x equal to a, then f is continuous at x equal to a. F is continuous at x equal to a. If f has a derivative at x equal to a, then f is continuous at x equal to a. So what we have here is that differentiability. Can't go that dark with our colors. Ooh, let's go on that one fast. All right, so we have this differentiability. Let's learn some geometry terms. Implies continuity. Alright, now, do you guys remember from geometry learning about conditional statements? Remember that word? A conditional. Does anyone remember what a conditional statement is? An if-then statement. So this theorem right here is actually a conditional statement. Any if-then is a conditional. And if you happen to remember from geometry, you would have learned this about second day of geometry. Or sorry, second week of geometry. That the contrapositive is going to be true if the conditional is true. So contrapositive is where we flip it and negate it. So if this theorem is true, if f has a derivative at x equal to a, then f is continuous at x equal to a. We're told that this is true. I can take the contrapositive, which would say if f is not continuous at x equal to a, then f does not have a derivative at x equal to a. And that is also true. So we're going to take away kind of a couple key things here. If it is differentiable, we know that it is continuous. Now notice differentiability implies continuity. It does not necessarily go the other way around. Just because a function is continuous doesn't mean that it's differentiable at that point. Okay? So this is a really important concept here, that differentiability implies continuity. So a function must be continuous to be differentiable. A function must be continuous to be differentiable. Now this is super important that you remember this. AP loves to ask questions kind of surrounding this. The function must be continuous to be differentiable. So if we are told that the function is differentiable, then immediately we know that it's continuous at that point. Okay. So differentiability applies continuity. In order for it to be differentiable, it has to be continuous. Yes?
I think there's a different word also for the slope continuous one.
Yeah, so both of these are the derivative, which means the slope of the tangent line at a specific point. This one is particularly at a specific point. This one, notice how it's at kind of f, so that'll give me the equation of this numerous slopes along my function. But we can use this one actually. If I were to use this one, I could then make it into an f prime of x just by replacing all my a's with x's. Does that make sense? A is just a point and number. Yeah. And likewise up here, if I did this one, I could find f prime of 3 by once I do this, then take 3 and put it in brackets. Or even from the beginning, take 3 and put it in brackets. Okay. Any questions on what we've said so far? Really, the idea is that differentiable means you can take a derivative. In order to be able to take that derivative, it has to be continuous at that point. Okay, now, here comes the big idea for today. Alright, so what does it mean then to be differentiable? We know that means you can take the derivative at that point. But how do we know that we can't? How do we know we can take a derivative at that point? A function is differentiable at point C. Function is differentiable at a point C. The function is differentiable at a point C. If we have the following. The limit as x approaches C from the left of f prime of x is equal to the limit as x approaches C from the right of f prime of x. So a function is differentiable at a point C if the limit as x approaches C of f prime of x equals the limit as x approaches C of f prime of x. So what we have here is, we think about this. Yeah, okay. I'm going to write. So I'm going to go ahead and rewrite these terms down to talk about that connection. Okay. So this is one of my limit definitions of a derivative. So our derivative is defined as this limit here. And so in order for my derivative to exist, that limit needs to exist. So let's think about that. This limit is the limit of that slope, right? We talked about how this is the slope of that secant line, and what this limit does, this is that slope of secant, what this limit does is it takes that distance between the 2 points and gets it smaller and smaller, closer to 0. So we end up having our secant line becomes our tangent line. So thus, when we do this limit, we're then finding the slope of the tangent line. That is what our derivative is. That's what we were talking about when we first learned this. So as my distance between my 2 points, as I bring this distance to 0, as h goes to 0, then this point comes over here, so where it is that tangent line. Alright, so again, my derivative is the slope of the tangent, and what that's made up of is the limit of that slope there. So if we think about it, in order for my limit to even exist, would you agree my left-hand limit and right-hand limit have to be the same? They have to equal each other. In order for my limit to exist, left-hand and right-hand have to equal each other. So my left-hand limit of this slope and my right-hand limit of this slope have to equal each other. So that's what our limit over here is saying. Our limit as we come from the left-hand side of that derivative of that slope must equal the limit as we come from the right-hand side of that limit of that slope. Alright? So again, think of this derivative means slope. So what this is saying mathematically, what it's saying in slang is slope on the left must equal the slope on the right side of the point. And again, we're talking specifically at a point. So in order for that derivative to even exist in the first place, since the derivative equals that limit, my limit has to exist. In order for my limit to exist, left hand and right hand have to be the same. Well, what are we taking the limit of? Our slope. So the slope on the left-hand side, again, the limit of my slope, that derivative on the left, must equal that slope of the derivative, or that slope, which is that derivative on the right. So that's how we can know a function is differentiable. If I don't have my slopes are the same, then that means it's not differentiable. Okay, so basically what it is my slopes are not approaching the same value, right? My slopes are different. So let's take a look at a couple of cases in which it would not be differentiable. All right, so an example, we have actually 4 cases we'll look at. Examples of not differentiable. So again, it has to have left-hand, right-hand slope are the same. So let's think of some cases in which my left-hand and right-hand slope would not be the same. Our first one, we're going to go back to algebra. Think of your function, the absolute value of x, specifically at x equals 0. Got my absolute value graph. And we've talked about this multiple times, how it's actually a piecewise function because the left-hand side is just negative x and the right-hand side is positive x. So if we're investigating at x equal to 0, when I look at my slope on the left, what is my slope on the left-hand side? -1. When I take a look at my slope on the right-hand side, what is my slope on the right? +1. Does -1 equal +1? No. So this would be an example where f of x is not differentiable at x equals 0. Now I could go over here to, let's say, x equals -3. It's differentiable there. Slope of -1 and -1. I could go over here to positive x equal to 1, +1, +1. So it's differentiable at those other points, but it's not differentiable at x equal to 0. All right. So this type we call a corner. That's our slang term for it, corner. So absolute value functions come at that corner. And we have that this is not differentiable. That is not differentiable at x equal to 0. Because that limit of our slope from the left does not equal that limit of our slope from the right. Let's say f prime of x. Okay. So that slope, that derivative on the left-hand side, my slope of that tangent line on the left is -1. That slope of that tangent line, that derivative on the right-hand side is 1. They're not the same, so it's not differentiable at 0. Right, so that one's corner. That's probably the easiest one to come up with on your own. Now this next one, you probably don't see as often with the functions that you've worked with so far. Your parent functions don't really have this. These are kind of funky looking graphs. So let's say we have a graph that looks like this. And we'll just say this is x equals a. So if we take a look at this one, coming from the left-hand side, what is my slope there? What do you know about it? It's positive, right? We know it's some decently large positive number. Now as we come from the right-hand side, what is my slope there? Negative. So we don't know exactly what the values are, but a positive number and a negative number don't equal each other. Our slopes are different here. So this is another example where it's not differentiable. This one we call a cusp. I like that one. What'd you say?
That description is not like the slang word.
I mean, it is, but it's okay to use it. It's not like the mathematical word. Corner, like corner and cusp are both okay to say. When you're referring to it on the AP exam, you can say corner cusp. They accept this last year. They had a question where there was all kinds of things said, and someone, I don't remember what they thought of it. It was a weird word, and they would not accept that. But they accepted corner. They accepted sharp point. They accepted. So corner and cusp are probably the most common.
How often do we
I don't know. It was really weird.
Did they accept you now?
No, like, it was an answer a kid had presented that they did not accept. And they said they had a lot of kids putting that, and so they don't know what to do. But anyway, so cornering tests, in fact, when you look in the calc textbook, those are how the phrases are. So. All right, so again, we have here, same reasoning, those limits of the derivative, or that slope on either side, are not equal. So we have f prime of x, and let me try again. F of x, my function, is not differentiable at x equal to a. Okay, so again, our slopes are different. In fact, if you look at the limit of your slope, it's approaching, kind of almost looks like it might be approaching. What type of slope is that? It's a Ooh, let's talk about that. That's actually our next situation that we're going to look at. So our third situation, think of just your cube root of x. So f of x equals the cube root of x, specifically at x equals 0.
Because what do we use can above?
Well, use inverse. Alright, so if we look at this graph here, it seems innocent enough, right? There's no corner, there's no cusp. So when we look at x equal to 0, and we try to draw our tangent line here, what type of line is that? A vertical. And what is the slope? Because remember, the derivative is the slope of your tangent line. What is the slope of a vertical line? It's undefined. So if I try to do my limit, and I don't even have a slope, my slope is undefined, then my limit does not exist, which means my derivative can't happen. So this is what we call a vertical tangent. Vertical tangent. And if we kind of look at what the slope is approaching on either side, again, we can see that slope is approaching that vertical line, which is what gives us that issue. So this would be another example where my derivative is not, my function is not differentiable at this point, whenever we have that vertical tangent. F of x is not differentiable at x equal to 0. Because for this guy, our limit as, what we're approaching 0, x approaching 0 of my derivative is undefined, so my limit doesn't even exist. So if that limit doesn't even exist, we can't take it. Yes.
The limit isn't 0 because it approaching 0.
What? What?
How come the limit isn't 0 because isn't it?
Good question. So this is the limit of the derivative, not the limit of the function itself. The limit of the function is 0. As I approach it, as I go towards 0, my values are approaching 0. But what we're saying is, what are the slopes approaching?
Okay.
So when you set notation of the derivative, that means take slopes. What are my slopes, my tangents? Right here, pretty flat. Good to go, good to go. We're going vertical. On the right side, flat. Good to go, good to go. We're coming vertical again. All right, now our last situation isn't funky at all. It's actually quite familiar now for you. Let's go ahead and draw a piecewise function with a jump. Let's make it this way. Alright, so this last case, remember that that theorem said a function must be continuous to be differentiable. Let's go ahead and call this one. Is my function continuous at A? No, so we don't even have to look at the limit of my slopes from either side. Because if it's not continuous, then it can't be differentiable in the first place, right? So this is just, oops. Okay. This is just simply it's not differentiable, but not because it's some weird case with our slopes, but rather because it's not continuous. F of x is not differentiable at x equal to a. Because f of x is not continuous at x equal to a. So no continuity, you don't even get to enter the world of differentiability. So again, our different situations that we might see where it is not differentiable is if we have our corner, like that absolute value graph, comes at a sharp point. We cannot draw a tangent line because there's no perfect tangent line for that. The tangent line does not exist for our cusp as well. Our vertical tangent, it blows up the world when we try to do that one, and our piecewise function is not even continuous, so we don't even get to enter differentiability at all. Now, interestingly, differentiability builds upon continuity, which builds upon limits. So if you think about it, in order for a limit to exist, we have to have the left and right hand are equal, right? Does my function have to be defined at that point for the limit to exist? No. We don't have to have the function value. We can have the hole there and still have the limit. But then to move into the world of continuity, what do I need to do? If my limits are the same, what else do I need to have in order for the function to be continuous at that point? Yeah, I need to have the function defined and be that same value. So it's kind of like, I've got my limit, but there's a hole. Come along continuity, in order for it to be continuous, I need to fill in that hole, and then it's that nice smooth curve. But then to move on to the world of differentiability, you need to have that it is continuous in order to even be differentiable. So for it to be differentiable, it has to be continuous. For it to be continuous, the limit has to exist, right? As well as that point being defined. So they build upon each other. Okay, we're going to go ahead. We'll just put it up here. Let's just draw a short little graph, kind of detailing some different options for differentiability or not. Here, nice and jump. Oops. I'll just read that. So this first one will be A. Jump here will be B. C. We got the roller coaster hill. Alright, I want you to go ahead and identify which of these are differentiable, which ones are not, and if they are not, state why. What do we get for A? Differentiable or not? No. What's our issue here? It's not continuous, yeah. Also, our slopes are definitely different as well. But it's not continuous, so already it doesn't work. All right, B, yes or no? No, why not here? Same thing. Again, not continuous. All right, C. What's our issue with C?
Different slopes.
Cost, good. And as well as it's the different slopes. Good. All right, now D, I did my best to draw this as a differential. No, and why not? Did we see a vertical tangent within here? I did my best to make it vertical. So D, it's also not differentiable because of that vertical tangent. If I try to actually find that slope, it's again the slopes are approaching a vertical line on either side.
I need to know where to draw the tangent line.
I know where to draw the tangent line.
Like, why do you decide, like, the slope rather than, like the curve on top?
Because D is here. So the tangent line is supposed to hit the curve at just one point, without like intersecting doesn't sound right. It hits the curve at one point. So like this is obviously easy to see. This one's easy to see, but we don't draw it perfectly. We're not going through the curve. We're trying to go kind of flat with it, if you would. Kind of like if you took just a flat board and let it roll down it, what would that board do? Yes. They're very similar. Corner, it's the same slope coming from both sides. Cusp that has more of that curve.
So that's what you use?
Yeah, not really too much, as long as you explain why not. Yes.
So if we're finding it, then we have to say why. Can we just say cusp or corner?
If it looks like it's the same slope coming on either side corner, if it looks like it's coming in curved cusp. Kind of like in elementary school when you would draw your birds in the sky like this, that's a cusp. Did you guys ever draw your birds in the sky like that? These are birds flying. Oops, that bird had 2 wings. That's your cusp, that curve. The curve coming to a point. Corners is like opposite that.
But on the test, could you say corner?
Yes, you're allowed to say corner, you're allowed to say cusp, you're allowed to say vertical tangent, and yeah, that phraseology is A-okay. Alright, other questions on this? Okay, so let's just take a look at one more problem, kind of connecting the limits, continuity, and differentiability. Actually, with this one down here, does the limit exist at A? Yeah. Is it continuous? No, that was our issue, right? So that's not differentiable. Does the limit exist at B? No, left hand and right hand are different. So if the limit doesn't exist, it's not continuous, it's not differentiable. C, does the limit exist? Is it continuous? Yeah, but it's not differentiable. And then D, does the limit exist? And it's continuous, but not differentiable. Good, okay. So take a look at this problem here. We've got a nice graph. And it says, where on the interval does the limit of the function fail to exist? Or does it fail to be continuous? Or does it fail to be differentiable? Where on the interval do you think that f prime of x, that derivative, that slope of the tangent line is 0? Okay. So take a look at those. Discuss this with the person next to you. Compare it with your shoulder partners or someone nearby and say, discuss what you think.
So B is 3.
Oh, Oh, and it's continuous.
Actually, maybe 0 is because the tangent point on the side for 0.
No. Cusp is always that sharp point.
So it's
Here we don't have vertical tangent, and I try to draw a tangent line.
Wait, is there something at that line that's at that point?
Just your derivative is 0.
Yeah.
So if you think about it, your derivative is going to be
so the slope is 0. So that's
Yeah, I don't know why I was doing
slope
I had some.
turn sideways in.
Yeah.
the tangent line.
All right. So the first one, where does the limit of the function fail to exist? What do we have? 5. Just one. Is 3 okay? Yeah, 3 is okay because the left-hand limit and the right-hand limit are the same. We don't have to have that function defined. All right. Where does it fail to be continuous?
3
and 5. Good. And where does the function fail to be differentiable?
1, 3,
Good. 1, 3, and 5. Why did 1 enter the picture?
because it's
Cusp. Good. And where on the interval do we think our derivative equals 0? At x equal to 0, yeah. So we know that derivative equal to 0, a line with slope 0 is just that horizontal line. And so when I kind of lay flat my pencil and trace it around, we've got flat at the top, look issues. Flat here, but it's not continuous, so we don't get to have differentiability. Positive, continuity issues. Sorry, that was negative and positive. So good, right here. It's a skinny little parabola, upside down parabola, but we do indeed have that derivative here. Okay, so any questions on that? Yes. No, so this is just a skinny parabola. It's not this, or piecewise absolute value is typically where your corners come in. So cusp is where it's kind of like the parabola got turned inside out, if that makes sense. Like I take these and flip them the other way around, kind of like a volcano. This is just a skinny parabola, we're good. As I'm getting closer, if I take this and move my pencil with it, it's getting closer to flat, getting closer and closer to 0. Its slopes go from positive to 0 and to negative to 0. Whereas with this guy, it's going kind of to that vertical tangent, if that makes sense. And with my corner here, it is the same slope. Those slopes are not progressing towards something. Does that make sense? So my corner, the slope is the same. It's not changing, it's not getting closer to each other, or a value in between. The cusp, I have basically my slopes are approaching that vertical line, which causes that issue. Here, even though my slope is negative, it is getting closer and closer to 0. And here, even though my slope is positive, it's getting closer and closer to 0. Do you guys see that difference between those 3 cases? Any other questions on that one?
So would you say that the difference between corner and cusp is that corner just has different slopes, but cusp is approaching does not exist?
Yeah. So that corner has the same slope for this half of it, and then the same slope for this half of it, but those slopes are not the same. The slopes are changing, but they're approaching that vertical tangent, which causes that issue. As opposed to the parabola, the slopes are so it's negative on one side, so positive on one side, negative on the other, but they're still changing closer and closer to 0. So they're approaching, as I move my pencils along on either side, they're both getting closer to that flat slope there. Whereas here, they're both going vertical. Here, they ain't changing to each other. Does that make sense?
So x equals 0 would be 3? X equals 3?
X equals 3 would not be what?
For the parabola, it's not
This isn't differentiable, but because of the continuity. Since it's not continuous, it can't be differentiable there. Now, if this was filled in, then we'd be fine.
for D, parabola.
because again, it's not continuous, we can't even enter differentiability. This means derivative. If it's not continuous, I can't have the derivative at all. I can't even consider it. So since it's not continuous there, you don't even get to consider whether or not it's differentiable, because it has to be continuous to be differentiable. Meaning it has to be continuous to have a derivative at that point. Other questions? Okay. So that's really the basics of differentiability. Now, next unit, we're going to be doing derivatives with polynomials, so you'll see kind of that. Our polynomials don't really give us issues with our derivatives. But later on, we'll have spots where it's so different. Right, so I want to just kind of recap and talk a little bit more with our limit definition of derivative and re-emphasize that we can use either definition of that derivative. I'm going to write it up here. We can use either definition of a derivative to find that derivative. Sometimes the H one's more helpful than the A and vice versa. So we're going to take a look at a scenario in which the A one might actually be better or the H one might be better. Now you've done a million of these with expanding and simplifying, so we're not going to do a million more. But I just kind of want to show you how the X approach A, what situations that one might actually be quicker than our H one. All right, so let's then, before we do that, go ahead and just recap that whole derivative. All right, so we know that our derivative, go ahead and write this down. Our derivative is that slope of the tangent line to the graph at a particular point. The graph at a point. So I have my function on my graph, pick a point, draw your tangent line, whatever this slope is of that little itty bitty tangent line. That is my derivative. Now, we've talked about how just a line is going to have the same slope the whole time, but other functions, like an x squared graph, your slope changes as you go through. Okay, and we talked about the different notation for our derivative. Again, we saw f prime of x is probably the most common. We have also y prime, but it's actually was saying that f prime of x tells you both what the function name is as well as what variable, independent variable you're using. Whereas y prime, it doesn't tell you what independent variable. Now, obviously, it's probably most likely it's x, but that's probably why we use the f prime of x more often. Now, we also saw the notation dy dx. In a way, look, dy dx. In a way, this is more informative than this guy here, because y prime just lets us know if we're dealing with the function y, whereas here we're saying we're taking the derivative of y with respect to x, so that lets us know what variable we're taking with respect to. We could also say, instead of f prime of x, we could also say df dx, because again, f is just the function name, so you might see that, but it's probably more common to see df prime. And then again, that last one that we talked about, ddx of some function, we're just going to put an f of x. But it's saying the derivative with respect to x of our function. Again, that tells us what variable we're doing with respect to. Whereas this guy doesn't tell us. Okay, so all those notations mean that derivative, which means the slope of the tangent line. All right, so slope of the tangent line to the graph at a point. And we talked about, as we were doing that circuits, how another way we can think of this is the instantaneous slope or instantaneous rate of change. Because again, that derivative tells me the slope at a point. So I can, at any point in time along that graph, I can pause time and say, what is my slope right here, right now? And then I can move just a little bit later, 1.3 later, and say, what's the slope right here? So it's at that instant, what is that rate of change? What is that slope? So that instant slope. So again, derivative, you might see that phrase, instantaneous rate of change. And then we also talked about, when we were talking about limit definition derivative, about velocity and how sometimes that's used to represent derivative. And we said velocity is the derivative of the position function. So again, velocity by itself doesn't just mean derivative, but it is derivative of something in particular. It's the derivative of the position function. So back in algebra 2, when you guys used quadratic models and said, if I throw the ball up in the air with the velocity or an initial velocity of 2 meters per second at a height of 5 feet, and then you had a quadratic to model that, that's your position. Where is the position of the ball in the air at any point in time? If you were to take the derivative of that, that would actually give you the velocity of the ball at any point in time while it's traveling in the air. What do you think the velocity is of the ball at the top of your parabola? 0, right? Because it slows down, stops, comes back down. And we'll learn more about that later. But so again, velocity you'll often see grouped with derivative because it is a derivative, but it's a derivative position function. And then we talked about last class too how there's a difference between instantaneous rate of change and average rate of change. So let's just kind of do a side note here. We have also average rate of change, which is not our derivative rate of change. This is different. So let's kind of break down the differences here between instantaneous rate of change and average rate of change. And again, we were saying that rate of change we can think of as slope, right? Rate of change is slope. It's that change in y over that change in x. Or our actual slope equation, y2 minus y1 over x2 minus x1. Going back to algebra 1, maybe even pre-algebra. So our rate of change is our slope. It's that change in y over change in x, change in value over some other change in value. That rate of change. At what rate is change in y? Is the y changing with respect to the x change? So rate of change is that slope. So that's why we said instantaneous rate of change is like that instantaneous slope. But what we're talking about is that slope of those tangent lines. We pause the function and say, what's the slope of the tangent line right here? Now our average rate of change would be our average slope. When we're dealing with average, we're talking about over an interval. So instantaneous is right here at this point in the graph, what is my slope? Average is saying over a time interval, or over this interval from x equal to 3 to x equal to 5. What is my slope or my average rate of change over that time? So my average rate of change, this is really slope between 2 points. Or you can think of it as slope on an interval, right? Because the 2 endpoints indicate what your interval is from x equal to 3 to x equal to 5. So my slope between 2 points is slope on an interval. Or if we think of it in terms of secant and tangent lines, it's really the slope of your secant lines. Because secant line, again, is a line that goes through 2 points. So if I take those 2 points and find the slope between them, it's the same thing as if I draw the line of those 2 points and find my slope of that line. Okay, so instantaneous indicates use derivative. Average means go back to algebra 1 and use your good old-fashioned algebra 1. Use this guy. Hopefully you have fond memories of algebra 1. And you're like, oh yes, let's go back to middle school and something. So instantaneous versus average are definitely different things. Instantaneous is my derivative. Okay. So we were given the definition of the derivative, not just in terms of words that just slope the tangent line, but in terms of how do we find that. We talked about how it is our limit definition of that derivative. So again, our limit definition of the derivative, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. So again, this means derivative. So the derivative of my function is whatever this limit ends up giving me. And then our other one that we had, f prime of a, which is the limit as x approaches a of f of x minus f of a over x minus a. And again, this means the derivative, but notice here it's the derivative at a specific value. So again, this is talking about the derivative at a point. Whereas this one will give you my derivative of the entire function. But again, we can use them interchangeably. And some of you guys did do that on your circuit activity, where when it asks for the derivative at 3, instead of using my limit definition with the h to find the full derivative and then plugging in, you went ahead and used f prime of a and took that point and plugged it in and found it that way. Now, when you're doing the derivative with the point already plugged in, that's only going to give you the derivative at that one single point. So if you're going to need to use that derivative again later, it's probably best to go ahead and find the whole function. But again, we're going to use these interchangeably. All right, so we're going to go ahead and take a look at the example as to why one might be better than the other. Okay. So our example here. The derivative of f of x equal to just 5x cubed. Nothing too crazy. Derivative of f of x equal to 5x cubed. Alright, now again, we can actually use either limit definition. I feel like h is probably the one that is most popular to use, but again, I'm going to show you how we can use each one. So if we use the h, let's just go ahead and set it up. We're going to set up each of these side by side. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And we're going to compare that to f prime of a is equal to the limit as x approaches a of f of x minus f of a over x plus a. Right, now, again, just like I said in class when we first learned this, if it's helpful for you to go ahead and draw a line, say work, identify what is my f of x plus h for this, x plus h quantity cubed, and then go ahead and simplify that all out beforehand. By all means, go ahead and do so, but I still need to see each step. It's meant to be neat and organized. But if you're able to just go ahead and immediately recognize, okay, well, I just simply replace x with x plus h wherever I am, feel free to do so. Okay? But if you choose to do that work outside, draw that line, label it work, and still show me all your steps for it. I will check that to support your answer. Okay, so if I go ahead and substitute in, make this limit for my function up here. H approaches 0, so f of x plus h would be 5 times x plus h quantity cubed. So that is my x plus h minus 5x cubed over h. What would have to be your next step? What would we have to do next? Yeah, we'd have to take this and do x plus h cubed. Is that x cubed plus h cubed? No, don't you do that. That hurts my soul greatly when people do that. You have to do x plus h times x plus h times x plus h. That's a pretty long process, right? Let's compare and see what it looks like when we use my x approaching a definition. We can definitely do this. It's just going to be a bit more work, but it's still definitely doable. So let's take a look at it for f prime of x with our x approaching a. So this would be the limit as x approaches a. F of x, which is just 5x cubed, minus f of a. So instead of a, instead of x, I replace it with a. Just like here, it said f of x plus h, so instead of x, I add x plus h. Here it says f of a, so I just simply put a. So 5x cubed minus 5a cubed over x minus a. Do we have to FOIL that guy out? No, in fact, it's already multiplied out, if you would, and already in a format that might make it easier for us to factor. So let's go ahead and continue on this side. Can I do, I see an x cubed, a cubed, and a difference there. Can I go ahead and do difference of cubes right now? What should I do first? Good, factor out that 5. Why can I not go ahead and do it with the 5 in there? Yeah, 5 is not a perfect cube. It has to be perfect cube minus perfect cube. Alright, so let's go ahead and do that. 5 is x cubed minus a cubed. Now that's going to be a lot easier for us to factor. And we can already guess that we're probably want to have an x minus a factor on top, right, to reduce with that bottom. Just like over here, we would have to multiply this all out. Ideally, there's some things that cancel, and then we can factor on each to reduce, right? So let's see how you are with your sum and difference formulas. These come into play a lot throughout the year. They kind of periodically show back up. So don't forget these. All right, x approaching a. So on my 5. I like to fill in my terms and then my signs. So cube root of x is x, cube root of a is a. First one squared, last one squared, multiply them together. And then so, same sign, opposite sign, is constant.
So we just kind of.
That's the pattern that I think through. Alright, so now we have this nice reducing here. And now I can actually go ahead and substitute in. I'm going to go and just write out the next step just so it's easier for us visually, but again, on a test, I trust that you can substitute in your head and ignore the x minus a's. But what we have then is limit as x approaches a of 5 times x squared plus ax plus a squared. So let's try direct substitution. Because if we would have done it up here, we would have gotten 5a cubed minus 5a cubed is 0 over a minus a over 0. So we'd have 0 is 0, which is why we had to go through all this. And now when I substitute in, what do I get? I get 5 times a squared plus a times a, so another a squared, plus a squared. What's a squared plus a squared plus a squared? 3a squared times 5, 15a squared. So this is what f prime of a is. Alright, so we've got f prime of a is 15a squared. But we weren't told to find it at a specific point, were we? We were told just to find the derivative. So I want f prime of x. So f prime of a is 15a squared. What's f prime of x going to be? Say x. Put it right here. 15x squared. Good. And that's your answer there. So you can use that limit definition with your a. It's just if it's asking for the overall derivative in the end, instead of f prime of a, you want to say f prime of x, because that's what it was asking for, f prime of x. Now, what if they would have asked us at a specific point? I'm going to take this up here. Yeah. Copy it for me down here. Okay, so let's change this up. Maybe instead of asking just for the derivative, it said find the derivative of f of x equal to 5x cubed at x equal to, what do you get? What number you guys want? Just one?
42.
Ooh, we don't want to cube 42 though. Can we just go like -3? -3? I want to throw in a negative. We want to do some work with it. Okay, so maybe they didn't ask for the derivative at all. They just asked for the derivative at a point. And this is a problem all by itself. You know you're not going to need the derivative again later on. Because on free response questions, a lot of times you need that information later on. But this is just a standalone. You don't get that derivative anywhere else. So we just simply want the derivative at that point. We don't need the whole function. Again, you can use either one of these options here. All right, so let's go ahead and set up each one and see which one we would prefer. So f prime of, I'm just going to go ahead and write out the original so that it's easier for us to fill in. It's not necessary for you to write this. You can go and start filling in the values. h. And then over here we have f prime of a. So as x approaches a, f of x plus h x over h. So again, up here we chose to go the a route because then we didn't have to multiply out all the x plus h's. Now you will have sometimes that if you try the a route, when it's all multiplied out, it's not so easy to factor. Here we had a nice, easy difference of cubes, easy to factor. Sometimes it won't be so intuitive as to how to factor it, and it might be then better for you to just, through brute force and sheer ignorance, as my one professor would say, just plow through this, take the time, actually multiply it out, because it would be easier to factor. So it's not always that a is going to be easier than h, but typically, if you have like something cubed, something to the 4th, 5th, or heaven forbid to the 6th, it might be better to do the a. Okay. But h sometimes is easier to factor, so it's kind of up to you to decide which way you want to go about it. Alright, so now we're looking for the derivative at x equals -3. We can actually go ahead and plug this in from the beginning. So if I look at my h derivative, I have f prime of -3 equals the limit as h approaches 0. This would be f of -3 plus h rather than x plus h minus f of -3. So again, I'm just taking -3 and putting it for x over h. Now for this one, when I actually go ahead, again, you could do work, draw your line, and identify what is f of -3 plus h. Let me go ahead and say f of -3 plus h. You can take that and substitute it in. 5 times -3 plus h cubed, so on and so forth. But again, you can just substitute straight in. Now when we substitute this in, f of -3 plus h would be 5 times -3 plus h, or h minus 3, cubed, minus, it's going to take -3 minutes, so -5 times -3 cubed. Now this part here is nice and easy to simplify, but what would we still have to do over here? We'd still have to FOIL it all out. So for this case, h might not be the better one. So let's take a look at a and hope that it's better. So if I set up f prime of -3 over here, I get the limit as x approaches -3 of f of -3 plus h minus f of -3. Whoa, what was I doing here? I totally wrote up the wrong formula, didn't I? Okay, let's try this again. Alright, we're in a, so it's f of x minus f of a over x minus a. Again, y minus y over x. Okay, so it'd be f of -3 minus, oh, no. It's a, yeah, thank you, f of x minus f of a. So a is -3 over x minus a, so x minus -3. So again, notice here on the left, you're replacing x with 3, so that's why I replaced each of these x's with 3. Whereas over here, we're replacing a with -3. So we replace only the a's. Alright, so now when we go ahead and continue on this side, limit as x approaches -3, f of x is just 5x cubed minus f of -3, so minus 5 times -3 cubed over x plus 3. You can tell that it's going to be similar to what we were doing above, right? Let's go ahead and simplify. Let's see, -3 cubed, -27. Plus, okay, we can do this. I can't store that much in my head, so I better. Alright, so 27 times 5, 5 times 20 is 100. 7 times 5, 35, 135.
135.
Can we do Ooh, it's not even a difference anymore, it's a sum. That's exciting. Can we do sum of cubes right now? Let's factor out 5. So actually, I think I said this last class, if we would have worked smarter, not harder, we could have identified here we'd be taking out the 5, and then we could have just left it as 27 or -3, but that's okay.
It was good to do that mental math.
Limit as x approaches -3. Take out my 5, so I have x cubed plus 27 for x plus 3. Again, we already have that kind of hint indicator that we're going to have something back from x plus 3. We're pros now. We have our second difference of cubes. X plus 3. X minus 3. X plus 3 squared, multiplied, same time on sign as well. Okay. Alright, so this looks very similar to what we did before. So now if we go ahead and take -3 and substitute in, because direct substitution up here would have given us that 0 over 0. And now if we try direct substitution, we get 5 times -3 squared is 9, minus 3 times -3 is 9, plus 9. So similar to what we were doing above. And we get, we're going to add 9 -3 equals 9 plus 9 plus 9 is 27. 27 times 5. Okay. Now, again, if it asked you, if your original question said, find the derivative, and then find the derivative at that point, you wouldn't do the limit 2 separate times, right? We would take our derivative we found here. We would take our derivative that we found here and then just substitute in -3, right? So if I took -3 here, f prime of -3, 15 times -3 squared, 15 times 9, 90 plus 45, 135. Right, so you wouldn't do the limit both times, but what I wanted to show you was that you can actually use this one that we normally use for that point. You can actually use it to find the entire derivative. And we could use the h1 to find our derivative at a point, but again, sometimes it's better to use the a. So here on this side, if I were continuing over here, I would again multiply out, simplify, and then I would actually substitute in that 0. And you would see that all my variables would go away and I'd be left with just a number. Okay. So again, you can use either function, or sorry, either limit definition, regardless of what the instructions are, whether you're finding the whole derivative or just a number. Any questions on that?
Sorry, just
Oh yes, sorry. Okay. That wasn't actually h isn't too bad when you multiply it out. It actually factors out pretty nicely. Alright, so again, limit definitions are, we can go either way. Now, on your circuits there was a couple questions, and we talked about this in class, but I kind of want to again recap it. Oh, and you'll see on the key for the circuits, because I care so much for you guys, that I would do the limit definition for you students. Alright, but on your limits circuit, yes, what's your question?
So, how much review is there, and what's better than the review?
All of it's fair game.
All of it?
Mm-hmm. It's over Unit 1 with our differentiability and review.
Is it a lot of review?
There's probably more calculus than review. Although technically limits are review. More heavily on the calculus.
So it's summertime?
That's fair game. Just check Blackboard for homework. Okay. So they would ask something like this. What is the slope of the tangent line? That wasn't bad. We knew that meant derivative. But then they would ask for the equation of the tangent line.
much?
Right, the equation of the tangent line to our function. And so again, we talked about in class how we know the tangent line is, the slope of that is our derivative. And in order to write the equation of any line, you need to use either y equals mx plus b or point slope form. Now, in calculus, we'll actually use point slope form more often. On the AP exam, they allow you to use point slope and just leave it like that, because that technically is an equation of the line. And if you really wanted to, you could use standard form, but that's the least desirable because it takes most work to do that. So the equation of the tangent line, you need both slope and a point. Well, we know that we can find our slope by doing the derivative, our limit definition of that derivative. So then when we do that, if we look, we actually had that from a previous problem, number 24. I'll go to work for that. So again, you could have either done the H limit definition or the A limit definition. And you got your slope was -1/6, I believe. So this is the slope of the tangent line. But to write the equation of the tangent line, I need to have the slope and a point. So they gave us one of our points. I think I might have gone too far. Nope. They gave us our point for x equal to -6. And we had from our previous problem that our slope, our derivative at that point was -1/6. But, so we have our slope, and we have our x value. Then in my point slope form, what am I still missing? Y. Yeah. So how do I find my y value? I've got my x value, I've got the function. How do I find my y value? You just plug it in. You take your x value, put it in your function to get your y value. And so that's what we got here. So then you have your slope, -1/6. We have our x value given to us, which is -6. And we have our y value we found, which is 3. Now, sometimes they'll be nice and actually give you the coordinate point, both the x and y, but a lot of times they won't be nice. They'll give you just the x, and you have to find the y. So what's happening here is, if I were to graph that function, let's see, it's been flipped and shifted to the right 3. So it looks something like this. All right. And they asked for it at -6. We'll continue this out here. Alright, so then what they're asking is they're saying, write the equation of the tangent line at x equal to -6. Well, here's my original function. Here's x equal to -6. There's that dot. Again, to know that point for my line, I have to get that y value. So if I draw my tangent, this would be the equation of that line, and we can see we have that really flat, or not so steep slope, because it's -1/6, up 1/6. So what they're asking is, this tangent line, at that point, what is the equation? And that's what we found here. We have our slope, because our slope comes from our derivative, and we have our point, because we've got the point x equal to 6, plug in and find your y. So when it's asked about the equation of the tangent line, think about what that means. Tangent line, its slope is the derivative. In order to write an equation, you also need the point, so you take them and plug it back in. Alright, now let's just go ahead and do one more IVT problem. Make sure you know all of your limit rules. Go back through that quiz. I'll know a lot of you guys were just making silly mistakes. So make sure you know your limit rules. Be careful with your notation. Make sure you know if it's top, bottom, balance, or bottom heavy in those rules. But be careful. We use top, balance, and bottom heavy only when we're looking at x approaching what? Infinities or negative infinities. That's our end behavior. So when it says the limit as x approaches 3, don't put 0 or your horizontal asymptote. Please actually try that direct substitution. If we try direct substitution and it doesn't work, what are our options of what we can do? We can factor. What else can we do? Say there's a radical in there. What do we do to get rid of that? Conjugates. If we have trig, we can do that. But try direct substitution first. Just because you see trig or some bottom-heavy rational function, that doesn't mean that we're necessarily getting those answers. Try your direct substitution. If direct substitution doesn't work, then manipulate it somehow. check to see what the limit's actually asking for. What is x approaching? Is it approaching a single number or is it approaching infinity? Okay. Remember those tricks, sine of x over x. That's when x is approaching 0. Right? So just be careful. Those limit rules, it's just what you did in pre-calc, but just be careful we're actually looking at what the question is asking for. Alright, so let's just take a look at one more IVT problem. So say it asks you, is any real number on the interval, let's go 0 to 4. Exactly 1 less than its cube. Okay, so is any real number on the interval 0 to 4 exactly 1 less than its cube? We don't even see the words IVT here. They're not even asking us to investigate a particular y value. They're just simply asking us this general question. So let's take a look at what this means. Is any real number on the interval exactly 1 less than its cube? So let's say I take a number, call it x. Is it exactly 1 less than its cube? So is the number itself exactly 1 less than its cube? How can we translate this? 1 less than its cube. Yeah, x cubed minus 1. Okay. So what their question is, does this happen anywhere on this interval? Okay. Well, if we move everything to one side, let's go and just subtract that x over. So I have x cubed minus x minus 1. Yes. We know then if this function crosses my x-axis somewhere, then that means that it satisfies that original equation, right? Now, with IVT, we have that special case where IVT basically says, if I have a continuous function, and my y values are different, so if I have a continuous function, my endpoints are different, those y values are different, and I have a y value fall within this range, there's going to be an x value that matches up with it. There's going to be an x value that falls within the x value range. Okay? And so the special case we looked at was if A and B were opposite signs, then that means it had to cross 0 somewhere. So we can apply that here. They don't ask us what the number is, they're just simply asking, is there one that exists? So what we can see is, can I use IVT on this problem interval? So we're interested in, does this function ever cross 0? Right? Does it ever cross 0? So IVT tells us if we have one of the endpoints positive and the other one negative, then yeah, it's got to cross 0 somewhere. So let's go ahead and check all of our conditions for that. We're using IVT to help us solve this problem. All right, so first of all, is my function continuous? Yes, it is continuous. Why? Yeah, it's just polynomial. There's no restrictions on x. All right, we've got to check our endpoints to see if they're different. So let's see. F of 0, negative 1, and f of 4, a little bit more work. 4 cubed, 64. Minus 4 minus 1. So 59. Alright, endpoints are different? Yes. Alright, so then that next condition we have to meet is that for our case, because we are interested in does it equal 0? Does negative 1 to 59 have to cross 0? Yeah, so we know right now we can apply IVT because it's met those conditions. Meaning that if it had to cross 0, from negative 1 to 59, then I have somewhere within my interval, somewhere between 0 and 4, where that actually happens. Okay? So let's go ahead and write that second condition. So we have gone ahead and seen this here, so let's just state f of 0. Make sure your negative number goes first. is less than, we are interested in 0. Because we're interested in where it is equal to 0. Is less than f.
Wait, why do we have to do that?
Because we set up our equation here. And so in trying to solve this, when we moved everything to one side, we said, well, hey, if this equals 0, then that's going to satisfy this here. If we can get this equals 0, then that means that this equation is 0. Because we just simply manipulate. I could subtract my x cubed and say, if I find that x cubed, or x minus x cubed equals -1, then I know that this equation works. We went ahead and moved to one side and said, well, this isn't quite so easy to factor, but hey, if I can find somewhere where this is equal to 0, then that means this occurs somewhere along. Alright, so now we've actually got to go ahead and make our statement. Because right now, all we've said is the conditions are met. But now we've got to say, yeah, we can actually make our conclusion. So now we can go ahead and say, by IDT, intermediate value there is a C value where we've got what? C is in between 0 and 4. So that f of C is 0. Thus, we can go ahead and make our conclusion. There is a real number on that interval, yada, yada, yada. Thus, there is a real number on that interval where it is exactly less than 1 less than its cube. Alright, your homework is up on Blackboard. It just practices some more differentiability and then stuff for your test. Make sure you review for that test. Know your limits, know your continuity, know your differentiability, and make sure you haven't forgotten anything that you've learned until now.
If there was something say that I should
Heavily study what we've learned here in class, but make sure you still know everything you've learned. If I ask you what is tangent of 11 pi over 6, you should be able to know that because I might throw that into one of my limits, right?
Do you ever have off, do you have a class for 7 inch here?
Yeah.
Like I have co-op with